Okay, in this video, I'm going to introduce an idea called a self-balancing tree or a balanced tree. Okay, so if you think back to binary search and the binary search trees that we looked at, we know that they're efficient to search as long as they're relatively balanced. But there's nothing guaranteeing that you don't end up with a binary search tree where one side of the tree becomes very long. Like this tree here on the left, there's nothing about binary search trees that prevent this from happening, right? If I inserted 1, then 2, then 3, then 4, I would grow this really long chain down one side of my binary search tree. And then if I wanted to search for one of those nodes, it would take a long time to get to the bottom of the tree. Basically, the height of my tree would become equal to the number of nodes in my tree, essentially. So that's bad. And if binary search trees can't avoid this behavior, that means some of the time they're going to have this really bad behavior, right? So the BST algorithm does not ensure balance. It does not guarantee that we get close to H equal log n. It doesn't promise us that. Interestingly, we just looked at the max heap where we always had a complete tree, and we did know that we were always really close to log n, right? So you can have trees that stay really close to that minimal height. Can we do the same thing for a binary search tree? That's the question. Can we get closer to that minimum height, a height of log n? Well, the answer is we can, and we should. Okay, so a self-balancing tree is one that ensures that the tree remains balanced as insertions and removals are performed on it. And so what that means is since it's balanced, you're not going to have one side of the tree that's really long and another side of the tree that's really short. It means both sides of the tree are going to be about the same length. That's what we're going for. But not just from the perspective of one node, from the perspective of any node. If you look at any node in the tree, then you look at both sides of its subtrees, then they're all going to be about the same length. And so if that's true for the whole tree, that every node is roughly the same height on either side of it, each of its subtrees has the same height, and that means we're going to have a really evenly balanced tree, and we're probably going to have a tree that's pretty short and not one that's just really awkward and long in one place. There are actually many forms of self-balancing trees. We're going to look at the AVL tree because it's kind of what I think is the simplest one, and it uses height to balance the tree on insertion and removal. So it's just going to have this little heuristic that says if at some node in my tree one side's a lot longer than the other, then I'm going to do some operations to make them more even. But there are also these trees called red-black trees, which are very popular, and they use red-black labels on nodes to guarantee the tree is balanced. And there's also this thing called a B tree. A B tree is not a binary tree. Everything we've looked at so far is a binary tree. A B tree allows nodes to have lots of items and lots of children. And it takes advantage of that to ensure that the tree is always balanced. Okay, we're going to look at AVL trees. Okay, so in summary, we prefer self-balancing trees because they can guarantee that our height stays very close to log n. There are many forms of self-balancing trees, and we're going to take a look at the AVL tree next.